My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 644. In this lecture, we will try to understand Lstm. So, to remedy some of the problems that we have seen in the previous lecture, we introduced a new type of RNN called Lstm, which stands for long short term memory RNN, because it can take care of long term dependencies as well as short term dependencies by using a very interesting idea. So before we go into LSTMs, let me revisit the diagram we have for simple RNN. I just draw this diagram where we have two inputs. We have XIT is one input, and we have OT minus 1, isn't it? OT minus 1 is another input. Actually, OT minus 1 is output from the previous layer, and we said we will sum of both of them, isn't it? Just I'm recalling what we discussed in our previous lecture. We said we have two weights here. We have weights W dash and we have weight W here. Just check the weights. You have W and W dash, isn't it? So we multiply this output OT minus 1 with this weight. What we did, we multiplied this OT minus 1 with this weight W dash, and we multiplied this input XIT with W, isn't it? And sum both of them. Actually, what we did, and then sum both of them, sum them up. We are simply summing them up, and then we have an activation function. Just see, we have an activation unit F which generates OT, isn't it? And this activation unit we will send it to other function G, isn't it? This OT also we will send it to other function G, which will generate output to YIT cap, isn't it? All these things we discussed in our previous lecture. Just I am recalling what we discussed in our previous lecture. So this is the structure that we have seen. Let's redo the structure. This is one possibility, but there is slightly modified version of this that I would like, I want you to walk through. Let me draw the modified version. The modified version looks like this. I have my XIT. Just see here. This is modified version. Here you have XIT here, and I have my OT. Isn't it? Here I have two weights W dash and two weights W and W dash. That's what is the equations here for this particular diagram? What are the equations for old one? Your OT. What is your OT here? Your OT is F of W XIT. This is W XIT. Just see, plus W dash OT minus 1. Just you are summing them up. What is my YIT cap? My YIT cap is G of this weight is W double dash into OT. This is old thing which we discussed, isn't it? I have two weights W. All these things we discussed, isn't it? I also have I also discussed YIT cap equal G of W dash OT. These are the functions that I had, isn't it? This is the model that I have seen earlier. This model we have seen earlier. Let's modify it slightly. Not a big deal. Small modification here. What are we doing here? Multiply OT with W dash. Just see here, what you are doing, OT with W dash XIT. Just see, this is XIT with W. Instead of adding these two things, let's merge them. This operation is called merging. What is this operation? This operation is called merging both of them. I will explain you what is merging exactly in a second. We send them to our F. We generate our OT, and of course we have our G here which generates YIT cap. Instead of OT, I'm assuming, I'm assuming in earlier slide I have written OT here. Instead of OT, I'm writing OT minus 1. Why? Because here I have written OT. Just there is a slight change in notation. Here is the small change. What is this merge operation? Merge operation means, look at this step. What are we doing? Taking these and taking these two. Which two? This and this, and we are merging here. And merging. We don't have this this symbol. Which symbol? Earlier we have this symbol, plus symbol, isn't it? Now we don't have plus symbol here. Here we don't have plus symbol. Earlier we had that plus symbol, isn't it? That we had. What does it mean? Let me write down the equation, and so that we can understand what we are doing here. Here is my OT is, what is my, I can write these two vectors. First, what is this? Just let me write like this. What is this? This is my vector xit. This, what is my first vector? This is xit. Just I am writing xit. This is not OT. This is OT minus 1. Just a small correction here. Xit OT minus 1. This is one vector. I will create a vector xit comma OT minus 1. I am concatenating these two vectors, and I am also concatenating corresponding weights. What are the weights here? I am concatenating these weights. This W and W dash. This is just W. These two weights I am concatenating. This W dash. This vector W dash comma W. This is one vector, and another vector is xit comma OT minus 1. This is xit comma OT minus 1 is one vector. Other vector is W dash and W, isn't it? This is a vector. I can concatenate these two vectors. Which two vectors I can concatenate? Xit OT. If you speak strictly, it's not OT. It is OT minus 1. Here I am concatenating xit. This xit is one vector. OT minus 1 is another vector. This is called concatenation. Just adding one after the other, not numerical sum. This is called concatenation operation. So what I will do here is, I will take my newly formed vectors. What are the newly formed vectors? One vector is, just see, this W dash W, this one. This is one vector, and another vector is xit comma OT minus 1. Here this is one newly formed vector. This one is one newly formed vector. This is another newly formed vector. We have two newly formed vectors, inputs and their corresponding weights. I will do dot product between these two vectors, W dash comma W. This is a new vector. This is new matrix, isn't it? Instead of earlier what we did, if you recall previous one, just see, if you recall, this is old one. This is old one. Old one, what we did? In old one, in previous note, this is old one. That is important here. In this is old notation. In old notation, instead of here we are summing up. Just see, here we are summing up. Instead of summing up sum operation, I am concatenating W and W dash. Just see, W and W dash. I am concatenating xit OT minus 1. This vector W xit, this particular vector is larger than xit and OT minus 1. Of course, this W dash comma W, this vector is larger than W dash and W, isn't it? I am concatenating xit and OT minus 1. My OT in similar manner, I am concatenating W dash comma W, isn't it? So the only difference here is what is the difference? Here we are adding, isn't it? I am repeatedly saying we are summing up here. In old notation, we are summing up here. We are multiplying them. Here we are forming them, we are concatenating, we are forming the vectors, isn't it? Multiplicate here, instead of summing up, what we are concatenating vectors, this concatenation of this vectors, isn't it? That's what we are saying. This particular matrix is bigger than W dash and W. This particular one is larger than XIT and OT minus 1. Why? Because they are formed after concatenation. This is also, I can say, this, just see, instead of sum operation, what I did here, just I am explaining here, instead of sum operation, here we had sum operation. I am concatenating W and W dash, just see W and W dash. I am concatenating XIT and OT minus 1, isn't it? This is your YIT. What is this? YIT cap equal to this is modified version of simple RNN, I can say, isn't it? YIT is essentially G of W dash of OT, isn't it? This is modified version of simple RNN. This is also simple RNN, modified version of simple RNN. Both of them are used. We will stick to this. We will stick to this particular notation. So that we will in future we will try to make use this notation, so that we will stick to this modified version, so that we can understand LSTM better. This one is preferred way of, actually nowadays people are preferring this particular notation. People are preferring this notation. So for this discussion about LSTMs, here is a terrific blog. Just see, this is preferred way of writing notation. There is a terrific blog by Christopher Ola. If you recall, we saw a lot of blogs by Christopher Ola, especially we discussed on principal component analysis and Tisney blog, isn't it? We understood a lot about Tisney from Christopher Ola. Even we understood a lot about principal component analysis from Christopher Ola blog. Christopher Ola, now research engineer. I think he is research engineer or research scientist at Google, working on deep learning stuff, isn't it? This is the blog. I request all of you to go through this blog. So this is his blog. It is written in maybe it's on August 27, 2015. I really enjoyed by reading this blog. It is the best blog on LSTM. It is the best blog I have read on LSTMs. Actually, my understanding on LSTMs improved dramatically after reading this blog, or I could say it is much more clear. Lot of times what happens is, when you first read a research paper, you get an idea of things, but still have some lagging doubts. It's still not clear for you. My clarity about LSTMs are really improved after reading this Christopher Ola blog, Understanding LSTM Networks. It is brilliant blog. The notation here, it is slightly different from the notation that we are used. Let me connect the dots here. Here what you have is, I will connect these dots in my next lecture, that is in lecture number 645. I request all of you to go through this lecture, and if you have any difficulty, please keep a comment. Thank you very much.